You are listening to the PFAS Research and Remediation podcast series, produced and created by Arcadis, with funding from the Environmental Security Technology Certification Program, ESTCP, grant number ER23-7692, through the United States Department of Defense. All opinions, interpretations, and conclusions expressed belong to the hosts and guests and do not represent views or policies of the Department of Defense, Arcadis, or guest affiliations. In this first season, we're focused on PFAS and interview a broad panel of experts who have each contributed to the growing knowledge base around remediating this emerging chemical of concern.
Today I'm speaking with Dr. Jennifer Field, a professor in the Department of Environmental and Molecular Toxicology at Oregon State University. Jennifer specializes in the development and application of analytical methods for organic micropollutants and their transformation products in natural and engineered systems, with a focus on PFAS. Her current work focuses on the development of PFAS fingerprint sources, characterization of PFAS in landfill gas, and PFAS on specialized textiles and other materials. She also serves as executive editor for the scientific journal Environmental Science and Technology. Today we will be highlighting her project ER 18-1259 titled A Mechanistic Understanding of PFAS in Source Zones, Characterization and Control, or in simpler terms, working to understand how PFAS move in the environment following release. Her research examines questions like, where do PFAS go following release, or how do they move in specific environments? I do want to start by saying that Jennifer is likely the reason why I got involved in PFAS. I was a graduate school student studying under Dr. Morton Barlaz at NC State, and she approached him about working on a National Science Foundation grant, looking at PFAS and landfill leachate on a national scale. They got the grant, and I happened to be the graduate student who was assigned to the project in Barlaz's lab. So big thanks to Jennifer for getting me involved in this. In fact, almost exactly a decade ago, I was fortunate enough to visit the Jennifer Field lab at Oregon State University, where she was doing the analytical methods side of our project. It was the first time I had seen a mass spectrometer, which is the standard instrument used to measure PFAS. She was so welcoming, and I am forever grateful for her start in my PFAS world. So, based on our history, I know you've been working on PFAS for at least a decade. When and why did you first start looking at PFAS?
So as a graduate student at the Colorado School of Mines, this would have been prior to 1990, I happened to be in my advisor's office and his telephone rang. And it turns out it was an elk hunting buddy of his from Michigan. And those two had a brief chat. And in the middle of that conversation, my advisor, Dr. Don McElhatty, turned and handed me the phone and said, "My elk hunting buddy has a question for you about fluorinated surfactants. Since you work on surfactants, maybe you could help him." So I took the phone and said hello, and it was in that very brief conversation that I was made aware that there was something known as a fluorinated surfactant. And so this person worked for a company at the time and had questions about what would happen to fluorinated surfactants. So I didn't do anything with that at that time, but I did not forget that conversation. And when I came to Oregon State University, of course, any new assistant professor is like, what on earth am I going to study? And I remember that conversation. I thought, well, that's kind of unusual. Maybe nobody else is working on it. And so it was a tip, really, very random, fortuitous tip. And I decided to look into it at that point at Oregon State University. And as luck would have it, and it influences our projects to this day, I began to collect various commercial reference materials. And some people might remember that the journal Chemical and Engineering News used to be distributed as a paper copy journal or, thin magazine. And inside there was those tearaway cards where you could write away for things. And there was a card to write away for fluoride kits of 3M. And so I wrote off for a few of those cards, and I got some standard reference materials that are just commercial reference materials, PFAS and other things, that showed up in these bottles, and I still have them in the lab to this day. So we started our collection of kind of weird and wacky PFASs, and they're still in our collection. We try to make use of them to this day. So that's the origin story for us.
Talking specifically about SERDP project ER 18-1259, it looks like there were three main objectives for this project. The first objective looks like comparison of PFAS interactions to a pristine soil versus interactions in soil coated with PFAS. So you're saying spilling PFAS on soil, which has already been coated, is different than spilling PFAS on an area where there's never been a PFAS release before. Is this what your work ended up showing?
Well, maybe we'll just step back a little bit. We're trying to understand or mimic or really study the relevant scenarios. So a lot of the AFFF, so aqueous film forming foam releases, date back to, well, probably the 60s. People did a lot of testing on military bases, it actually depends. There's not great records, so it could have been fairly high frequency, perhaps weekly, monthly, maybe some installations only yearly, but that high frequency of training with these complex products in single locations meant that sites for firefighter training receive repeated doses, not just one, whereas a crash site might have been a one-time incident, one-time application. So we recognized in the portfolio of field sites, there's probably a variety of sites that received only one AFFF versus these multiple repeated. In addition, there are sites that only saw AFFF by itself. So for example, there was an NFPA testing requirement where the trucks and delivery equipment had to be tested with some sort of frequency. And that was just simply, could they deliver AFFF diluted at appropriate application strength to a field site? That actually does not involve fuels or flammable, so no fires involved. So you might just have AFFF by itself, but it might have these repeated applications. There were also, probably even more frequently, was the actual firefighter training. And that's where flammable fuels, solvents, waste solvents, were collected, lit on fire, and then doused with AFFF. So under those scenarios, you would have repeated applications, but now they're commingling with fuels that, as we all now understand, if you have sufficient release of fuels and other solvents, you end up with non-aqueous phase liquids. So our project got going trying to understand what would happen when an AFFF hit pristine soils and sediments, which would happen today if there was a crash site. But we also thought that scenario does not apply to most of the aged sites where the last AFFF may have been applied in the early 2000s. So it's really sort of turning back the hands of time, trying to understand some of those formative applications and what was happening at that time in terms of retention of PFAS or PFAS, because it's more than just PFAS, during those scenarios and then those subsequent applications. We're trying to look at scenarios and also really embracing the complexity of a full-on AFFF. So in our study, we have not used single compounds at low levels. We have used intact AFFF formulations with all of their complexity, with all their other co-constituents at application strength.
So you think when you conduct experiments using the full mixture versus maybe one or two individual PFAS, that probably influences the ultimate results?
The classical technique in column studies is to conduct what you call breakthrough curves. So you look at what's in the initial solution being added to the column. We call that C0 or initial concentration. And then you measure concentrations in the effluent over time to get yourself a breakthrough curve. And you can see beautiful breakthrough curves in the literature when people use soil or sand, single components, and lower concentrations. Beautiful classic breakthrough curves where the concentrations C over C0 equals 1. And then you also see the concentrations dive down, and you can do analyses on those curves to obtain retardation factors. In our case, when column studies were done with sand or real soils from various horizons, and you apply the intact AFFF, you do not get beautiful C over C0 breakthrough curves that look like classic textbook. We get very low breakthrough. We get a very significant retention of mass, and breakthrough curves are very low and diminished, which means that a lot of mass is being retained even in a sand column with no organic carbon. The reason this is important and relevant to the call for research in this topic area is to really try to understand why and how PFAS are being retained in source zones to a greater degree than one might expect otherwise, or perhaps based on other contaminants. Dr. Konstantinos Kastarelos down at University of Houston, which is an expert, he did some really interesting mixing experiments and showed that as fuels and AFFF at application strength meet each other in the subsurface, there's sufficient mixing energy to get some really interesting phase behavior, meaning we start with 2 phases, but we ended up with 3. And that third one has a milky white color, and it turns out it's a mixture of L-napple and a lot of PFAS. And so a lot of the PFAS goes into that thermodynamically stable microemulsion in that middle phase. It's gel-like, so high viscosity. We didn't really see that coming. What this means to us that makes sense is AFFF, it was designed not to mix with fuels. It's designed to create a coating when foaming on a fuel to blanket the fuel surface, cut off the oxygen supply, knock back the fire, and prevent reignition. And one of the questions that still endures to this day and why we have a follow-on project is there any evidence of these microemulsions or these gel-like phases? And where is there evidence?
So in the ground, where would you think the PFAS would interact inside the subsurface with NAPL?
So once Dino had done these shake tube tests to demonstrate this formation of this third gel-like phase, he then moved on to a series of column experiments where he just took pure sand, kind of knocking out the influence of organic matter, pure sand, and he placed jet fuel A to create what's called a residual, so just L-napple occupying some of the pore space in a saturated column setting. He then added AFFF application strength, really trying to mimic what was actually applied in the ground. He flowed AFFF into that system and then monitored the pressure and also monitored the effluent. And quickly, after less than, I think, about 1 pore volume of AFFF, a significant back pressure created to the point that the column flow stopped. And this was evidence that the flow dynamics had changed radically by flowing the AFFF into this L-napple residual. Back pressure would be consistent with the formation of a stable microemulsion and gel-like phase, such that the column flow stopped and the amount of PFAS recovered in the effluent was relatively low, or certainly not the breakthrough that one might expect from textbook images of breakthrough. So that's what happened under constant flow. He then did a constant pressure where he adjusted the flow to maintain the pressure. Again, back pressure formed, a separate experiment, brand new column, in place the jet fuel, tried it again under constant flow. Again, had to stop the experiment because the back pressure was building and concern was he would break the glass. So 2 independent experiments showing clear evidence that those scenarios may have happened in the field, and it's that mixing energy upon infiltration that may have given rise to these microemulsions that we see out on the lab top, on the bench top.
So I want to talk a little bit about PFAS precursors. As many people have probably heard, there are thousands of PFAS, but we typically only measure 40 or less. A lot of the other PFAS precursors or parent compounds in the degradation pathway do transform into something we're measuring. What are your thoughts on these unmeasured PFAS and how they're going to impact our understanding of movement of PFAS in the environment?
So if we go to an ESTCP project led by John Cornick, we were a participant. Colorado School of Mines was a participant, and it was a series of field characterizations. We did a very detailed spatial survey, both soil, sediment, and water, groundwater. And analytically, the Higgins lab and my lab tackled the chemistry in soil and sediment and water to really try to understand and document the occurrence of not only target PFAS, but as many suspect PFAS, so those are PFAS for which we have an idea of their structure and their mass. Thus, we can, with some degree of confidence, report their occurrence in soils and sediments and water. And so what we learned from that project and all 3 sites that we examined, that these zwitterionic, so those are PFAS that possess more than one charge on them. So the target PFAS that most people are familiar with are negatively charged. We have our instruments set up to see negatively charged PFAS. But when we talk about precursors, that just means PFAS that have more in their head group. So not the fluorinated chain, but we have more different kinds of atoms, a variety of atoms in the head group. And it's a head group that carries charge. Those head groups can have negative and positive charges. We call those zwitterions, borrow a nice German word, having 2 charges within or more within the molecule. And what Anastasia Nickerson, who was on the mines team, found is those are largely bound to the sediments very near the source zone. Because of their charged state, which is overall neutral and or in some cases positively charged, they don't travel far. So that might change how we view remediating and the total mass of fluorine that we need to address, because as those suspects sit in that source zone over decades, as they have done, they may be slowly transforming to the products that we see down gradient, which are the more soluble, more mobile, dead-end products that are targets. And so we're using fluorine NMR down at the Oregon State NMR facility to characterize the fluorine content. And that kind of draws a frame or a boundary around the total fluorine. And then with gas chromatography and liquid chromatography, mass spectrometry, we're trying to color in that frame and understand what we know and what we don't know. So in terms of discovery, NMR is guiding the discovery, and then we're trying to use advanced mass spectrometry tools to fill in that space to have the broadest understanding of what PFASs are out there and what has entered the world. And then, of course, the next question is, what became of them at those field sites if we discover significant groups that we didn't know about before?
I don't know if you have any results yet, but do you expect, our typical analyte list to make up most of the total fluorine signature in these foams?
Oh, that's a really great question. So a subset of our AFFFs, I don't know, maybe 25 or so, we did the total fluorine by NMR, and then we conducted the target analysis using one of the EPA methods. And I think there was like 14 on it, not the 40 right now, although we might end up redoing that. And even if you expanded the list, we found that you can only account for less than 1% of the total fluorine in the fluorotelmer AFFFs, and around, it's a higher amount for the 3M.
What do you think are the major questions about how PFAS move in the environment which haven't been answered yet?
Part of our SERDP project, we had examined the processes by which PFAS are retained at the air-water interface in the vadose zone. So in just the last few years, we now know that there is a mechanistic reason of why PFAS, especially the longer the chain, the more hydrophobic, the greater the tendency to accumulate at the air-water interface. And there is a lot of air-water interfaces in the vadose unsaturated zone.
So when I think about the Jennifer Field Lab, I don't just think about you. I actually think about all the great students that you've also produced out of your lab. What is it like for you to see your previous students go on and become researchers themselves?
It's super rewarding. I think aging sneaks up on you. You don't realize, time flies, when you're having fun and you work with super people, whether it's your own people or collaborators. And, we're really lucky here to have a super great people funded by SERDP and ESTCP. I have to say it's become a community of sorts, and we're really lucky that way. To realize you have had a cumulative impact in training young people, it's very satisfying. I have to say, being full professor and, kind of putting all that business of tenure behind you and not having those pressures, it really is just about getting students where they want to go professionally and personally at the same time, having whole lives and whole people, often with families, sometimes not. It's very gratifying, and you can really put all of your resources and all your attention on helping people get where they want to go.
Is there anything else you would like for the listeners to know?
You asked a question earlier about transport and uptake. So when we find suspect PFAS in surface waters, we have a problem. And especially if we find it in biota, like say fish, for example, we can't answer the question of what is the toxicity of those compounds. No one can, because there are no standards. That's one of the challenges the minute we find a suspect, of course, it's reasonable to ask, what does this mean for human health or ecosystem health? In the case of PFAS and PFOA, ecotoxicologists can purchase sufficient quantities of these molecules by which to conduct their assays, whether it's zebrafish studies or dosing avian or terrestrial organisms. And so you have to have a standard and sufficient quantities of sufficient quality to do that. So when it comes to suspects, we're kind of stuck.
I know the EPA requires pesticide companies to submit samples of standards, not only of the pesticide which they're trying to register, but also every known intermediate and byproduct of that pesticide sample. They don't require this for PFAS or AFFF. How do you think it would change if you had standard availability where the EPA could say, here is what is being manufactured as well as its byproducts?
Well, standards, that's everything, right? So that's where quantitative methods come from. That's how you would get an analyte onto a method 1633, which requires that very high quality standards become available. Those kinds of standards in sufficient quantities are necessary for toxicologists and ecotoxicologists to conduct the kind of screening and toxicological studies that to inform risk assessment. So those are key to so many things. Making standards is a very costly, very specialized type of thing, and we're very dependent on the availability of those kinds of standards. So it would open the door to many kind of studies that are just simply not available today. Because to discover compounds takes a lot of time, takes a lot of expertise. So it would short circuit a lot of those discovery processes. I do have to say, when we have to discover through mass spectrometry and environmental samples what's relevant and important, that is using a lot of taxpayer money to discover things that if your scenario were applied to PFAS, those barriers would be reduced and the time to data and understanding would be shortened significantly.
Hey, thank you. I appreciate it so much. Thank you so much for listening. This podcast was funded by ESTCP and recorded by Arcadis. The interview was conducted by myself, Dr. Johnsie Lang, and our guest today was Dr. Jennifer Field. If you're interested in more information on Jennifer's project, please see the ESTCP website for project number ER181259. If you have conducted your own research on PFAS and are interested in sharing your work, please email Teresa Gillette at teresa.gillette@arcadis.com. That's THERESA.GUILLETTE@ARCADIS.com. And please keep an eye out for more episodes coming soon.